Hello friends, continuing with our processing maps module. Okay, already we have seen about deformation mechanism map and processing map. Processing map we generated using a model called dynamic materials model. Okay, and in the same continuation, okay, we are now going to look at some microstructure and application. Okay, that how processing map can be used to and then validate through microstructure, okay, and then how we can use these ideas of processing map for some application. Okay. So, one usual way you will see how processing maps are used to kind of or how we validate the processing map, at the same time how we interpret the processing map. Okay. So, you can see here that again deformation temperature is on x axis and strain rate is we have taken a log on y axis, okay, and your contour maps are drawn, okay, and instable region is shown at these two location, okay. And now they have taken samples from different location, okay, wherever they are seeing higher efficiency, okay, and also the unstable region. Okay. So, you can see that wherever the high efficiency regions are there, for example 8, okay, 8 is here, you see more or less a nice microstructure. Okay. Of course, it must have seen some grain growth also. Similarly, here also you can see in this one also you can see some nice high angle grain boundaries are there, okay, and looks like a recrystallized microstructure to me. Okay. So, all this region 3, 4, this 3, and here I think you can see some partially recrystallized grains, okay, forming on the boundary. Okay. So, 4, 3, 4, 5, okay, all these are usually high efficiency region, okay, 8 and 9 also. So, 8 is here and 9 is here, okay, more or less recrystallized microstructure. Okay. Whereas, if you see the 2 here 1 and 2, okay, you can see that there are some flow localization has taken place. You can see some big elongated coarse grain and then some very this dark bends kind of thing. Okay. So, this usually happens because of the flow localization. So, this 1 and 2 you can see some kind of flow localization, okay, whereas other cases you can see the relatively nicer microstructure. Okay. So, this work was done in commercially pure titanium powder compact. So, powder was sintered, compacted, and then the deformation was performed on this powder compact, and from there these microstructures have been generated. Okay. Some more pictures, again this is a kind of a collected large number of processing map and microstructures were collected, and a book was written by the authors were Y.V.R.K. Prasad, okay, and from there I have taken all this. Earlier also we have taken all the processing map from that book. Okay. So, this is a magnesium zinc manganese alloy. Okay. Again you can see some processing map is generated, some efficiency contours are there, and you can see the unstable region. Okay. So, one microstructure is from this region where you have high efficiency 38%, and one microstructure is taken from the unstable region. Okay. So, you can see very clearly a very nice recrystallized microstructure here, okay, whereas here you can see lot of flow localization has taken place in these areas. Okay. So, this is where the instability must have been instability is occurring, okay, whereas in this case you can see a nice recrystallized microstructure. This is of the same alloy. Okay. This was in different condition. I think this was homogenized and this was in S cast condition. Okay. So, S cast condition you can see that there is a breakdown of dendritic structure is taken place, where you have got this high efficiency. So, this area is where you have got the high efficiency. So, from this particular processing condition a microstructure is taken. So, you can see nice wrought microstructure, whereas at a higher strain rate and lower temperatures you can start seeing some flow localizations here. Okay. And in the unstable region you can see maybe some kind of void formation here. Okay. Some these dark regions. Okay. So, this kind and the microstructure is also looks like a acicular microstructure. You can see this kind of long elongated grains or acicular structure. Okay. Whereas, in this case you can see very nice recrystallized equiaxed microstructure. Okay. So, this is for the same alloy, but in aced cast condition. The earlier one if I am not wrong it was in homogenized condition. Okay. This is another alloy, okay, stainless steel 304. Okay. You can see a very large unstable region is shown here, okay, and the efficiency is high in this particular area around 32% or so, and there you can see microstructure. Of course, it has lot of these straight boundaries, okay, and these are actually twin boundaries. Okay. So, these are not defects. Okay. Sometimes defects also looks like that, okay, but these are of course twin boundaries in austenitic stainless steel. Okay. And of course, the microstructure is again recrystallized. Okay. So, there is no issue with this microstructure. Okay. We should get in this processing condition I should get this kind of microstructure, whereas in the unstable region where it is at higher strain rate and lower temperatures, okay, you can see lot of flow localization has taken place, okay, all these dark regions. Okay. So, flow localization means the deformation is concentrated in few weak areas of the material. Okay. So, that is what you can see here, flow localization in the material, whereas you in this microstructure I do not see any defect like that. Okay. Another example microstructure and how processing maps are validated. Okay. So, this is one region where you have high efficiency, again a very nice recrystallized equiaxed microstructure. Okay. Of course, grain size is large. Okay. This is again a magnesium lithium alloy. Okay. Whereas, if you see at higher temperatures you can see some cracking at the grain boundary. Okay. Some void formation, void must have nucleated and they have kind of connected with each other, some cracking has taken place at the grain boundary. Okay. So, though it shows high efficiency, again we can be should be concerned about this, that it shows high efficiency, but there are defects in the material. Okay. The efficiency is around 60% here, okay, whereas it is 58% here at lower temperature. So, with increase in temperature you have new type of defects, and you can also see if I am not wrong that there are some cavities have formed here, okay, in maybe on the grain boundary or so, okay, and you can also see this kind of cracking or kind of a cavities joining together, and you have cavity coalescence kind of phenomena. Okay, and maybe some wedge cracking also must have taken place. Okay. So, the idea here is, though it does not show an unstable region and it in fact shows a very high efficiency region, okay, but still you can get defect in the material. So, for any processing map, okay, it is usually advisable to do a validation. So, all the high efficiency zone you should take microstructure of all the high efficiency zone, as well as few microstructure or few samples from the unstable region or unstable region, and one should do a good microstructural analysis before this processing map can be used. Okay. Now, there are some applications we are going to see for processing maps. Okay. Before coming to that, I just wanted to show you that what are the strain rate range for different bulk deformation processes. Okay. So, you have rolling, okay, you have forging, and you have extrusion process. Okay. And the average strain rate of these 3 processes is given on the x axis. Okay. So, for extrusion, if we are using hydraulic press, the strain rate is in the range of 0.1 to 10 per second. Okay. For impact extrusion, okay, very high velocity extrusions, okay, the strain rate is in the range of 50 to 200 per second. Okay. In forging, you have different types of forging. So, you have slow hydraulic presses. Okay. Through hydraulic press you are applying the compressive load. The strain rate is in the range of 10 to the power minus 4 to 10 to the power minus 3. For hydraulic press, okay, it is around from 10 to the power minus 3 to 1. So, or I think it is 10 to the power minus 2 to 1. Okay. Then there are mechanical presses, okay, used means I think they must be using some cam or some gear arrangement. Okay. So, these are not hydraulic. So, in mechanical presses you can achieve higher speeds, okay, and the strain rate is in the range of 1 to 30. Then there are hammer forging. Okay. So, under the gravity force, okay, a hammer is kind of dropped on the material, the strain rate in the range of 10 to 200 per second. Okay. So, again a very wide range of forging strain rates. Okay. Then there is rolling mill or rolling. Okay. So, there are 2 rolling operations usually. One is called what we call as roughing. Okay. There the strain rate is in the range of 1 to 20. And then there is a finish rolling, which is in which case the strain rate is around 10 to 120. So, roughing you usually do in the initial phase of processing. So, after the ingot casting you have made big ingots, okay, you want to roll it. So, initial, and these are done usually at high temperature. So, there you have roughing, you want to impose higher strain rate, higher strain, okay, to the material. And then when it is coming to the final shapes, okay, which is now going to go out for to sell in the market, okay, there we do finishing operation. The strain are usually low in this case, of course, the strain rates are high, but the amount of strain you put in one pass is quite low, okay, and the deformation is usually at low temperature, or usually it is cold rolling. So, room temperature rolling. Okay. So, just to maintain the good finish of the surface. Okay. So, only you apply very small amount of strain, okay, and you try to give whatever shapes you want to give to the material. Okay. So, these are called finishing operation to give a good surface finish to the material. Okay. These are the strain rate range. Okay. So, now we can use these ideas. Okay. So, now we have established that processing map are able to predict the microstructural changes which we want. Okay. So, it is able to predict that where you will have recrystallization, where you will have defect formation in the material. So, now that is now established. So, I do not have to keep looking at that again and again. So, now I can use the processing map for my other purpose, that how I can apply these processing map in actual application. Okay. So, for example, rolling of a microalloyed steel is if you are trying, you can construct a processing map first. Okay. You can look for high efficiency regions. Okay. So, of course, again you have to look about the cost of any process. Okay. So, I cannot do it at a high temperature because cost of heating the material will be involved. I cannot do at very low strain rate because then my productivity will be affected. Okay. So, you can see that a temperature range, okay, and a strain rate range is kind of defined for rolling. Okay. Because you can also understand that when you are doing any operation, unlike a laboratory experiment, okay, the strain rate, temperature keeps changing during the deformation process, okay, because these are continuous deformations sometimes. Okay. So, I have to have a large window in which I can do the rolling process or any deformation process. Okay. So, one way to use processing map is like this. Another in this process optimization was done in commercially pure aluminum. Okay. So, as I was telling you that these are continuous processes. So, the material is heated in the furnace, and then there are couple of or maybe 3-4 rolling mills are there. So, material is going from one rolling mill to another rolling mill. Okay. So, the temperature is continuously coming down during the deformation process. So, this open circle is the initial process applied in an industry to do the processing of aluminum. Okay. And after the processing map was generated, it was found out that the two conditions are coming in the unstable region. Okay. So, again to have good productivity and you do not want to have large heating. Okay. Of course, the first pass is here. Okay. And this is my last pass. So, 2, 3, 4, 5, 6, 7, 8. So, this is the last rolling pass. Okay. So, from high temperature my material is continuously getting cooler and cooler. At the same time, the strain rate of the deformation is also increasing. Okay. As you are going to multiple passes. Okay. So, the temperature was more here, strain rate was low, and then the temperature is coming down and the strain rate is increasing. Okay. So, this was the initial process. So, you can see that the unstable region is there in the last passes. So, maybe there can be a defect can be introduced in this particular condition. Okay. So, to optimize the process, the another process was proposed. Okay, these dark circles. Okay. And again you can try to see that they are trying to maximize the productivity by going to very high strain rate. Okay. And they are starting from a temperature of 500 degrees Celsius and going up to 300 degrees Celsius. Okay. And just trying to avoid this unstable region here. Okay. And not entering into this particular unstable region. Okay. So, that is how you can design a new process if you notice that the earlier process is going in the unstable region. So, this is what we can do is process optimization. This is for a Inconel 600 alloy. Okay. You have different operation. So, forging will be done at higher temperatures. Okay. As I told you, rough rolling or forging will be done at high temperature. Okay. And then the finishing operation will be done at lower temperatures. Okay. Again you can see we are just avoiding the unstable region and trying to have maximum strain rate which can achieve in this particular process. The carbide dissolution is taking place somewhere here. Okay. So, you knowing all this microstructural changes, now you can design the process that what should be my forging or finishing operation, so that there should not be any microstructural change which I do not want. Okay. Avoiding the unstable region and so on. This is for a magnesium zinc manganese alloy. Okay. So, you can see the difference between a homogenized alloy and the forged alloy. Okay. So, this is so you please understand that this is a homogenized material. So, after casting, okay, you have done the homogenization. So, still the dendritic structure will be there, but the homogenization what it will do, it will have homogenize the material, the chemical composition will be same throughout the material now. Okay. But still the dendritic structure will be there, and with that kind of as received material you have done different test, okay, to measure the stress and strain as a function of strain rate, and from there you have developed this processing map. Okay. This one same material after homogenization you have forged it. Okay. So, now this is forged first, and then you have again done the same kind of test as you have done here. Okay. Compression test. Okay. Measured stress at different strain rate and temperature. Okay. And from there you have generated the processing map. So, you can see that as you have done one forging. So, now you have brought the material into a wrought condition, your unstable region has shrunk. Okay. Here the unstable region was very big, covering a large processing window, whereas this unstable region is now kind of limited to a very small processing window. Okay. So, now it has opened my processing window for the alloy by doing a forging operation. Okay. So, you can understand that by doing these kind of initial operations, what we are trying to do is we are trying to have material, okay, in which you will have less chances of having defects. Okay. So, this unstable region is reduced by doing a forging operation, and again processing map is generated for this forged material. Okay. So, later processing now can be done for using this processing map. Okay. So, what we have done here now is we have used dynamic material model to develop processing maps. Okay. And using that understanding, okay, and by knowing that these processing maps are able to predict the microstructural changes from the efficiency map and the instability map. Okay. We have now confidence in that, and now we have used those processing map for different applications to design a process, to find out the processing window for different material. Okay, and to identify that what type of processing should be done for the material. Okay, you can use it very dynamically. Okay, and it will be a very good input for a process engineer. Okay, if you give this processing map to him, and he will be able to understand, okay, where he has to done the processing. Okay. So, this is important application of processing map. Okay. So, in the next lecture we will try to see there are some other models which people have proposed to develop processing map. Okay. So, that we will see. Okay. And then we will do again a case study in the processing map. Okay. Thank you.